Let's start. Good morning to everybody and welcome to the Severo Ocho colloquium. Our speaker today is Dr. Anna Guseva. Anna received the PhD from the University of Bremen in the year 2018, and her work was based on magnetohydrodynamic instabilities in accretion disks. In 2018, in fact, from the year 2018 to the year 2020, she got the first postdoctoral research stay working on a scale interaction in turbulence and working at the School of Aeronautical and Space Engineering in the Universidad Politécnica de Madrid. By the way, she speaks perfect Spanish. That is great. In fact, she was working with the Professor Jimenez Sandin as a part of an ERC project called Control. In the year 2020, she was awarded with a Marie Sklodowska-Curie postdoctoral fellowship grant, and she developed her Marie Curie project that was called Dynamical Mode on Non-Linear Properties of Astrophysical Dynamos at the School of Mathematics in the University of Leeds in UK. And currently, she's holding her third postdoctoral stay, working as postdoctoral fellowship at the Paris Observatoire, and focuses her research on numerical and data-driven modeling of stellar dynamos in the context of star formation. Today, she will talk about modeling of large-scale magnetic field in low-mass stars. And really, Anna, thanks for coming. Okay, and the floor is yours.
Thank you very much for the introduction. It's a pleasure for me to be here at IAA and to give this colloquium. So really, thank you very much for inviting. And today I will present my work on magnetic field dynamics and mechanisms of generation in low mass stars, so in stars predominantly with convective envelopes. So I will be speaking today about convective dynamics. And this work I'm doing at the Paris Observatoire in collaboration with Frédéric Petit-Demange, and also in collaboration with Charlie Pinson at the IAS at the Université of Paris-Saclay, and also within a larger ANA Prométhée project in collaboration with Evelyne Alessane, Catherine Dougalos, and Benoît Commerson, so which is funded by French National Research Agency and is devoted to study of basically star formation and different processes that accompany this. So just to present you with the outline of what I will be speaking about, first I will present you some context of stellar magnetism, why is it important to study it. Then I will tell you a few words about the modeling setup and aims of my work. Then I will present you with results of basically two sub-projects that I have been working on. One is about generation mechanism of magnetic fields, the dynamics, interaction with differential rotation in convective stellar envelopes. And the second one is about already stability of these large-scale magnetic fields already in a relation to three main sequence stars, so young stars. Let's start with the context. So we are interested in stellar magnetism because magnetic fields can really affect all physical processes in stars. From star formation, because they can direct accretion of the matter on the protostar. They are source of stellar activity, which is important, for example, for the planetary detection. So we need to model their dynamics and evolution. And they are also source of transport. So they exert magnetic stresses internally that can slow down stellar rotation. They also are source of stellar winds that can also affect and slow down rotation of stars. And so all these processes are in general of interest of ANR Prométhée. In particular, my part of the work is focused on this part. So what happens in a stellar convective envelope of a low mass star during a particular state of its evolution, let's say. And so there is a lot of observational data on magnetism in such stars. Most of this data come from spectropolarimetric observations. So by Zeeman Doppler imaging, we can reconstruct stellar magnetic field topology on large scales. I put here an example of such reconstruction for young T-Tauri star. So we can assess the distribution of magnetic energy for different spherical harmonics, large spherical harmonics at the surface. So, for example, a typical spectrum of such reconstruction you can see on the figure on the right, where their energy that is contained in different harmonics is compared to the total energy of the reconstruction as a function of L. And so some of the stars have predominantly dipolar magnetic field, for example, from this solar-like sample, which means that L is equal to 1. Some of the stars have a combination of dipolar and quadrupolar fields, which means that you have equipartition of energy on degree L1 and 2, for example. And you can see that the energy of this reconstruction quickly decreases with L. This is not because there is no energy at these small scales. This is because the reconstruction is limited due to the cancellation of small scale features. So basically, if we're looking at magnetic field of a star with spectropolarimetry, we just see the large scale fields and large scale dynamics. So how do this magnetic field look like? Well, from recent spectropolarimetric data, for example, there is a huge database from Donati group and from Spiro instrument. We more or less were able to map the different topologies of magnetic fields as a function of stellar rotation period and stellar solar mass. So this is a very complex diagram, which is frequently referred to as a confusogram. But I will try to explain to you in just a few words. So first, you can see here that there are different magnetic topologies existing, from predominantly poloidal field in red to predominantly toroidal in blue. And also the bolder symbols represent axisymmetric fields, and thinner symbol represents non-axisymmetric fields. So basically, stars that rotate slower are more likely to have axisymmetric predominant field. The stars that rotate fast. The stars that rotate slower with the higher masses can have more diverse magnetic topologies, while there is also an interesting branch with a new data emerging that shows that actually slowly rotating stars can also have quite a large poloidal fields. And so all these wealth of magnetic topologies are currently not yet well understood. And so one of the main objectives and aims of my work is to be able to provide models, dynamical models, numerical models, mathematical models for existence of such different zoo of magnetic fields. On the other hand, these fields are not stationary. They also have their dynamics. And this has been also quite well recorded in different stellar activity factors, and also with spectropolarimetry. So if we record magnetic fields with a spectropolarimeter at different years, for example, from 2007 to 2013, we will see that this low mass star, Cygni 61, has completely flipped its dipole from dipole orientation, passing through a quadrupolar phase. So we see some dynamics, we see some changes. The same from the Williamo paper, where already a solar-like star changes its dipole orientation on the time scale of around 4 years. So quite rapid changes. How are they produced? Why are they produced? How do they affect the properties of the star? What do they do, for example, the stellar to the stellar winds? What do they how they interact with the differential rotation? We all have to. These are all open questions that we have to answer. How do these magnetic topologies, magnitude depend on stellar parameters? how do they affect stellar activities? For example, the distribution of spots and what causes these magnetic reverses. And to answer all these questions, we really need to understand the generation of these fields in low mass stars, which means to understand the dynamos, the dynamo mechanisms, the dynamo theory, and build a dynamo theory for generation of these large-scale fields by convective stellar envelopes, if we are speaking about magnetism of low mass stars. And in principle, because dynamo is a complex nonlinear phenomena that can change considerably as a star evolves from pre-main sequence to main sequence, we need to understand it at different epochs of stellar evolution. So this is more or less the motivation to the work that I will present today. By no means I will answer all these questions, but at least I will show you my contribution to this motivation. So to the modeling setup. I'm using the classical dynamo model of stellar convection, which means anelastic MAC equations. So Navier-Stokes equation for momentum conservation, induction equation for magnetic field, and also entropy equation describing the evolution of energy in the system. I use a polytropic reference state, which means I can introduce effect of density gradients across convective envelope, which is presented here. So we have inner sphere and outer sphere that contains conductive fluid where convection is developing due to a presence of the entropy gradient. So in a short, you have a hotter inner sphere and colder outer sphere, and this drives convection. Okay. The simulation that I'm doing are done with the publicly available MAGIC code. That's a huge DNS software by Gastin and Lich. I use stress-free and insulating boundary for magnetic field. And there are, of course, many parameters that govern the evolution of this equation. These are very complex equations, but I will highlight just two of them that will be relevant for my talk. One is the Rayleigh number, which is basically proportional to the entropy gradient that drives convection, and therefore shows the strength of convective motions. And another one is the density stratification. So it's a logarithm of the ratio of the density at the inner and at the outer sphere. So how much of the density contrast we have between within stellar convective envelope. So the important thing here is that in the real star, these numbers are really high. So both the turbulence is really strong, so we estimate the Rayleigh number to be really large, up to 10 to the 20, and both the density contrast is really strong. And so, before I go to describe any results, I want to show you just a few slides about the classical dynamo theory, about the factors that can influence the large-scale magnetic field, in particular dipolar fields. We are interested in dipoles because they are frequently observed with spectropolarimetric, for example. And so one of these factors is related to the competition between inertia, so the forces that are generated by turbulent convection, and Coriolis force, which comes from the fact that we also have rotation of the system. So the setup that I just showed to you, in this setup, both inner and outer sphere are rotated with the same speed, which drives a Coriolis force and which models rotation, global rotation of the star. And so this ratio can be described with a Rossby number. So it's a parameter that consists of the RMS of turbulent convective velocities, the length scale of these turbulent convective velocities, More. Okay, so going to the another parameter, the stratification of the system, so the ratio of density between the inner and the outer sphere. I will show you two plots. One on the left corresponds to the results from the stellar evolution code. So you run equation for stellar evolution, different stages of stellar light, and we can plot the density as a function of stellar of the radius, basically. And what we can see here that the density contrast is quite large. So you can see up to 10 orders of magnitude between the inner parts and the surface. So basically, in the simulation, it's typically really hard to model this density contrast. And I will show you in a second one. On the other hand, there were, of course, a lot of works that try to do that. For example, the work by Reno, 2015. And what they basically show, if they plot the stability of the dipolar mode as a function of the density contrast and the function of Rayleigh number, this domain decreases as they go to high stratification. So the question is basically, a typical star is not located here or here. It would be located over there. So the question is, how stars, stellar convective envelopes, can maintain this large-scale dipolar fields given the strong Rayleigh number, so strong inertia, and the strong stratification. And this is the particular question that I aimed to address in this part of the work. So we developed really highly stratified and highly turbulent models in order to answer this question. So with stratification from n-word to 2 to 6, which means density contrast from 7 to 400. And also with a Rayleigh number much larger than the critical Rayleigh number that is needed for the onset of convection. And so let's go to the results. First of all, I want to show you which effect stratification and turbulent convection has on the length scale of turbulent structures in a convective envelope. So I compare here two simulations. One is weakly stratified and strongly turbulent, and another one is strongly stratified and strongly turbulent. And what you're looking at is the contrast of vertical vorticity at two different radii in the domain. So in the bulk, on the top, and on the surface on the bottom. And while for weakly stratified case, the length scale of the flow is more or less the same for both cases. And you can see some turbulent motions that doesn't seem to be very rotationally constrained. For strongly stratified case, in the bulk, you can see the development of more rotationally constrained convective columns as compared to the surface, where the convection scale is really small and no longer rotationally constrained. So if I put this in the context of parameters that I showed to you before, so the Rossby number, the ratio between the inertial and Gauss force, that can be measured not only for the globally for a star, but also as a function of radius. So if you, this is how it would look like. So let's follow this dark curve for n-word 6 and radius to radius critical 32. So this is how it looks like. In the interiors, this parameter is much smaller than 1, meaning that Coriolis force wins over. And in the surface, you have a surface layer, which is turbulent, which is highly turbulent, where inertia wins over, and so on. And development of such surface layer, together with rotationally constrained interiors, is the joint work of both stratification, so and and enhancement of turbulence. Because, for example, we can see how the surface becomes more and more turbulent, and the interiors become more and more rotationally constrained with increase of nρ. On the other hand, for weakly turbulent cases, the surface turbulent surface layer does not develop. So it's really an effect that needs both of these factors to be present. Now, what about magnetic fields? Well, we should not observe any dipoles, right? Well, in principle, these are diagrams. These are butterfly diagrams. So azimutally averaged magnetic field as a function of latitude and rotation time. So this is rotation of the star. For these two cases, for weakly stratified and turbulent, and strongly stratified and turbulent. And in black line shows the dipolarity parameter that I just showed you. And you can the difference between these two cases is that the first one shows more or less disorganized, weak, mostly quadrupolar dipolar waves with a very weak dipolar component on the large scale, okay, compared to first 11 harmonics. While the strongly stratified case has a prolonged periods of predominantly strong dipolarity. And this dipolar mode has its own dynamics. So, for example, if we follow it in time, we will see one reversal of dipolar field, another reversal of the dipolar field, then loss of basically of the dipolar field, and onset of the multipolar magnetic field configuration, and then a recovery of the dipole here, then again a reversal, and so on and so on. So if we continue this time series, we will get a good statistics for this process. The problem is that the simulations are really, really expensive. So this is the statistic that we have to work with. Now, this is what this field would look like if we look at the entire simulation. So the total magnetic field at the surface as compared to what they would look like if we would filter on the surface, as we would look, for example, with the spectropolarimeter through one of these reversals, through one of these dipolar events. And so, well, what you can observe is, despite that the energy is distributed on a large amount of scales, and the spectrum of magnetic field is really filled, but on the large scales, the behavior is not far away from what is observed with the spectropolarimetric. So you have magnetic dipole that is oriented in one way, then multipolar configuration during magnetic reversal, and again after that reversal of magnetic field topology. And from the statistic that we have, we see that if you take for example, average solar rotation rate of 28 days as a reference, this changes of magnetic topology take place on a time scale of a few years, from 4 to 8. So in principle, this depends also how you define the reversal event. But in principle, this is in agreement, generally in agreement with spectropolarimetric observations that exist. And so, if we then measure the strength of the dipolar mode as a function of our parameters, so the normalized Rayleigh number and normalized density contrast, in both cases, we will see that for strongly that the dipolarity of the model increases both with Rayleigh and with nρ. While for the flows that have weak stratification, this doesn't happen. So it seems like if we really would push these models towards realistic stellar regimes, we would achieve even stronger values of dipolarity and more pronounced dipolar mode in our domain. And so now the question is why? Why do we observe this effect? What we found out, this is related to several mechanisms, several physical mechanisms that are present in a stratified turbulent convection. And one of them is the compression of magnetic field lines by anisotropic stratified convective motions. What happens is that if we have a density contrast, then in the induction equation, there is additional term, there is additional mathematical term that's responsible for advection or compression of magnetic field together with convective motions, in particular, radially directed convective motions. In other words, if you, for example, compare the strongly stratified and strongly turbulent case with a case that is also stratified, but not as turbulent, and if you compare the distribution of velocity, convective velocities, so radial convective velocities in colors, and the distribution of magnetic field lines, in contrast, what you will see is that you have a good correlation between magnetic field lines and strong negative convective plumes. What happens is that due to this anisotropy of stratified convection, the downward plumes are stronger than the outward plumes, here in blue. Despite occupying less space, they compress magnetic field lines and they direct them inside the stellar interiors. Okay, and this process gets stronger as we get to both to high turbulence levels. This anisotropy gets stronger as we get to the high turbulence level and high stratification. For example, this is if we plot the joint probability of radial distribution of velocity and magnetic energy, so radial magnetic energy, what we will see is that this probability contrast gets more and more skewed towards negative values. So basically, we have strong convection at the surface. It produces magnetic fluctuations. And as we go to strongly stratified regimes, most of these magnetic fluctuations are transported by the negative, are generated and transported by the negative convective motions. So it's a large-scale axisymmetric process that, on average, takes this magnetic energy and transports it into axisymmetric dipolar mode. There are, of course, different other metrics that can quantify this process, and one of them is, for example, the Poynting flux. So from magnetic energy equation, we can look at this quantity. And if we plot this quantity as a function of the radius of the convective envelope, we basically see systematic enhancement of this flux, especially at the surface where we have the strongest stratification and the strongest convection, both with convection and with enhancement of stratification. And this is what we think contributing the most to the strengthening of magnetic dipole. So this is what in mean field dynamo theory is called typically magnetic pumping. So just a couple of words about the dynamics of this field and the interaction with the zonal, with the differential rotation. The interesting part about these models that I find is that we observe dynamical interaction with differential rotation, which I plot here as zonal flows. So it's the azimuthal component of the flow. axisymmetric, so averaged over phi as a function of the radius and coordinate here during both. So this is during the dipolar period, so when dipole is strong. And this is during the multipolar periods where the dipole is lost. And the lines here shows the distribution, the two-dimensional distribution of quantum flux. So it appears that during the dipolar period, the distribution of zonal flows is three layers. It's three-layered. It's mostly solar-like because actually our simulations are very close between the transition between the solar and anti-solar rotation. Nevertheless, so for this case, what we see is that we have a positive prograde jet developing at relatively high radii with the relatively weak retrograde flow on the surface and even weaker quiescent inner region in the domain. And this is the region where the magnetic flux is predominantly accumulated inside this zone. It is called tangent, and this is where the dipolar mode is promoted the most. Okay, and during the multipolar periods, we do not observe that. So there, the surface retrograde jet increases in strength and takes more space, and the positive jet moves towards the inside tangent cylinder towards the lower radii. And so we can measure that. So we can measure the maximum of this prograde jet as a function of time. And we can compare it with the total evolution of the magnetic energy. This is what I show here on the right. And what you can see here that we have, it's aperiodic, but this nevertheless deterministic oscillations between the two states, between the state with the relative low total magnetic energy, where the dipolar mode prevails, and we observe this three-layer rotation configuration, and the state with high magnetic energy, anti-solar differential rotation, and more or less equal energy distribution over different spherical harmonics. And so this is very interesting because in principle, these dynamical variations of shear, of surface shear, if you want, together with variations of magnetic topology and variations of total magnetic energy, could provide additional constraints of the type of the dynamo behavior in low mass stars with thick convective envelopes. So just for recap for this part of my talk, first, what we have observed is that we have identified the mechanism, potential mechanism, large-scale magnetic field generation in these dynamos. And we have also identified the parameter regimes in which we can seek for models of such dynamos in order to describe the different dynamics and topology that is observed for stars with different masses and rotation rates. So in principle, it's a really good start for systematic study of such processes. And also, we can see that the dynamics that is presented in these models, at least on the large scales, can give us a good way to determine which the most to provide additional constraints on the dynamos in real stars, and also to determine the models that are more likely to have all physical ingredients for the stellar dynamos of the dynamos. Now going to the magnetic field stability in the three main sequence stars. The motivation to this part comes from the fact, from the observations that different magnetic topologies exist for the same stellar parameters. I'm showing here quite a new data from the SPIRO, from the Donati group, that shows a magnetic field for slow rotators, where basically we can see that for the same parameters, we can have both large scale poloidal fields, axisymmetric fields, and non-axisymmetric, so small scale. Okay. A similar problem exists for high mass stars, where bimodality of magnetic field is observed, either strong or wavy. And this can be related, this process can be related to the fact that the dynamo is really nonlinear phenomenon. And so depending on the initial condition, we can have different solutions of combined Navier-Stokes induction equation, and therefore different magnetic configurations. And so the idea of this part was to go more beyond the analysis of the mechanism of magnetic field generation and to apply these results to actually stellar evolution. The idea is very simple, is that the condition of small change in the condition during the star formation can destabilize dynamo and magnetic topology. For example, you can have a different distribution of rotation, you can have accretion shocks, you can have a hotter and colder region on the surface of the protostar. So there are many things that could go wrong or right, whatever you pick up. And so the setup is as following. Towards the rotating spherical shell that we have already seen, we introduce additional perturbation and rotation. So we rotate the inner sphere a bit faster than the outer, because the outer sphere, remember that we are in star formation, so we have rotation, we have accretion disk, and so which constrains the outer surface of star to rotate with it. And so this gives us a new parameter, so shear Rossby number, which is the ratio between this difference in rotation, so omega shear in this case, to the global rotation of the system, to the strength of the Coriolis force field. Another addition that we make is that we implement realistic gravity measurements. So in collaboration with Louis Manchon and the Paris Observatoire, we take the gravity profiles from the early state to the late stage of stellar evolution from the Cézanne code, and basically implement it in the inelastic model and see how the dynamo reacts to this change. So this is these are the limit cases that we study. So one is basically gravity inversely proportional to radius, so point mass gravity profile for the late stages of stellar evolution. Another one is from the early stages of stellar evolution from the Cézanne, more or less approximated by a polynomial. And the third one is the linear gravity profile, where the mass is more or less equally distributed over the values. And so we also take a relatively low density contrast, which from at least from the simulation of Louis can show from the simulations can be shown that this relatively low density contrast is a good approximation for the dynamo, at least in the large part of the convective zone, at least for the early stages of the stellar evolution. And these are part of this result for the gravity profile from Cézanne. So the stars measure the surface dipolarity as a function of rotation time, starting with no rotation and the dipolar field here on the top, slightly perturbed until the dipolar field loses its stability, begins to oscillate, and eventually transforms into the multipolar magnetic field topology. So the question is, when does it happen? How strong do we have to rotate, basically? How strong the inner core of a star during speed in order to maintain or lose the dipole moment? And so we plot the dipolarity for the different gravity profiles. So the first thing that we can see is that the shear Rossby number is perhaps not a good parameter to measure this, because the curves are relatively spread. What we really have to compare is the strength of the shear to the strength of convection, to the strength of the convective mechanisms that generate this dipole moment. And indeed, if we plot the dipolarity as a function of this parameter, we can see most of these curves, both for point mass, so later stages of evolution, and for realistic gravity profiles, they more collapse with the criteria for collapse at around 0.1, say 0.15. And so this gives a good proxy for whether, if we know the rotation of rotation profile of a star during its evolution, it gives you a good proxy whether it's likely or not that it will maintain its dipole. Okay. So the last thing is what happens with G proportional to R. What happens with this curve? Why does not behave as the rest? And the answer is in a dynamo mechanism, actually. Because if we compare the distribution of convection, so again, the local Rossby number, and the distribution of rotation. So here I'm already looking not at the global Rossby number, but at shear Rossby number, but at local shear Rossby number on the right. What you can see is that convection for the two gravity profiles from Cezanne is more, in this case, the convection is more or less equally distributed across the whole domain, from the inner sphere to the outer sphere. It's, in this case, the dynamo is generated globally in the convective shell. On the other case, for the linear gravity profile, most of the domain is inactive for the dynamo because the convective is stronger at the outer shell, and this is where it generates most of the helicity, and therefore is the source of generation of magnetic field. And if we compare it with the distribution of the shear Rossby number, what we can see is that rotating the inner sphere creates strong shear near the inner sphere. So in this region, which is called tangent cylinder, basically it creates a retrograde jet. And so if all the dynamo is generated somewhere outside, over there, this means that we need a stronger rotation in order to disturb such velocity. And so a local criteria for this process is more appropriate. So this is something that currently I'm looking at. And so for discussion, I just added one more point. So basically we get a criteria for collapse of dipolar fields for initial condition of the three-main sequence stars. And the question is, so you will ask me, okay, this is all very theoretical. What about observational constraints? And so this is part of the reason why I came here, because one of the most interesting observational constraint that we can have is actually magnetic activity. It's actually to look how these different magnetic topologies and dynamics that we observe, how do they translate into the changes of, for example, factors such as photometric activity proxies. Because we know from the studies, from the Kepler study of low mass stars and stars with different spectral types, from lower to higher, but stars with convective envelopes, that there is a correlation between stellar mass, stellar temperature, and stellar rotation. And so the idea is a bit to develop a collaboration with IAA to disentangle the contribution of different magnetic effects in terms of sunspots, flares, different surface effects from the surface convection, and the pulsation in one particular type of stars, so the F-type stars, so that have a higher mass in this sample, both through fractal analysis of light curves in time series and through numerical modeling of magnetism and convection in this thin convection envelopes. And this is what I could contribute. So this is be in collaboration with Fabian Pascual and Stella Variability. So I thank you for your attention, and I will be happy to take questions.
And for questions, we have a few minutes for that. Right?
Thank you for the very nice talk. I had a question about the first section 3 of your talk. When you showed that map of the magnetic field you compute with all the scales versus the blurry helicals less than 5, I think, reconstruction.
Yes.
The map.
This one, yes.
I understand that your well, you have all kinds of approximations behind your model to get those top maps, but if you improve that, like ideal, I come to you with a map as you have here on the bottom from observations. How likely it is that you're able to say this matches this distribution rather than that one? What are the statistical steps needed, and what other observations maybe you would need? Is that a reasonable prospect even?
So one of the things that can be directly compared is basically this distribution of the spectral distribution. So this is something that can be compared. The spectrum of the magnetic field as a function of spherical harmonics, both for spectropolarimetry and for the model. Another thing that could be really helpful is longer spectropolarimetric campaigns, which is usually quite difficult to do because to observe this magnetic dynamics, we need to observe the same stars for during several years. But nevertheless, if you have a dynamical information about magnetic field distribution over time, and if you compare it to different epochs, and if you see similar dynamical behavior, this could be another say confirmation that okay, this model is doing good and this model is doing not good.
But there's no hope to get more spherical harmonics from the observations to compare with more refined maps that you already compute.
So from this point of with respect to spectropolarimetry, the problem is that small scale fields, so small scale harmonics, they produce cancellation in these reconstructions. So I know of work that try to, for example, to go the other way. So you suppose that there is some distribution of a small scale magnetic field, and then we see, okay, this is what it would, to see which changes it would produce to the reconstruction. This work by Koshikov and the latest.
Thank you.
I have a question about the new results from the night. Can you go the slides?
Yes.
Confusing around?
The ones that I showed up.
Yeah.
Okay.
That one. So I might miss it, but in your simulations, you did it for fully convective stars or for partially convective?
So this is for partially convective stars.
So the results where you study the stability of the dipole field is for partially convective stars, correct?
Well, in principle, the reason why we do partially convective stars is because doing fully convective envelopes is really computationally expensive. So with the fully convective envelopes, we wouldn't be able to go as far in parameter space. On the other hand, the the mechanism of the dynamo, they're quite universal. So the same, let's say, dynamics of magnetic field and the same topologies the dipole topologies are obtained both in thick envelopes and in fully convective.
The difference here is that in fully convective stars, you almost never see, correct me if I'm wrong, I think it might have changed a couple of years, but you see the topology evolution of the magnetic field in partially convective stars. You never see it in fully convective stars, because fully convective stars are, so if you take snapshots of the global magnetic field topology and fully convective stars, you see mostly dipoles that are stable on the time scales of decades.
Yeah.
So you don't have reversals there. Therefore, the dipole is stable there, right? If you go to partially convective stars, you start seeing these messy diagrams where magnetic field evolves. The large scale component of magnetic field even flips sometimes. In some cases, but in most cases, it's just very unstable. So
Yes.
and you don't see dipole, strong dipoles either, right? So the question here is, why do you? So why do we need this strong stratification and density and to have your dipole be stable? Because even from earlier simulations from Rakesh Yadav, for example, from 2015, he actually showed that you don't, with his models, I don't know if his models were like full star or like a shell models, making shells. But I think the conclusion was that you see this mess what Donati group sees now in the stars with long rotation periods, just because of the period because of the Rosenthal. As when you go to low Rosenthal, so for fully fast rotating, fully convective stars, this is where your dipole is stable by simply because strong rotation generates strong field, which benches the evolution of this field, so it's not possible to change anything. While in this region where there you have slow rotating stars that generate very weak relatively weak magnetic fields, this is where you expect to see polarity changes and cycles. This is when cycles starts to appear in low convective stars. And what the question about this diagram is this diversity of the topologies that you see, is it because of cycles, or is it do you think that some stars here can be flipping their topology with time, even if they are fully convective?
So in this case, with respect to this diagram, I think these are quite new results. So I don't know if the stars have been observed consistently for a long time to observe actually cycles. So in
well, for instance, GJ410 at the left side, I think it's been observed for a lot of years now. So there are some stars that have decades of observations at the bottom.
Well, I think it's a really good various points, and the novelty of our work, compared to, for example, the work of Yadav, is not only that we model these dipoles. Of course, we can. It has been known for a long time that if you set up the parameters right, you can obtain dipole magnetic field in different geometries. The thing is that according to the properties of convection, we would expect the different layers of a star with a different density distribution have different influence of inertia as compared to the Coriolis force. And so from the point of view of dynamo theory, if you have strong inertia, then you will destabilize the dipolar field. And so basically, the question that we posed to ourselves was a bit inverse. Okay, we observe from the point of observations, there is a strong evidence, there is a dipolar field. This is no question about that. The question is, from the point of view of dynamo theory, how is it possible? Because how the simulations that have been we have seen before were unconclusive in this case. So if I go back,
But for example, simulations of Rakesh,
Yeah.
they had a dipole self-consistently in this fully convective fast rotating surface.
yes,
So
yes.
There was no problem to have dipole in the first place. I might be missing here some, but you say that you need a strong stratification to have
In
stable.
their simulation, the Rossby number that they report is quite low. So the Rossby number that they report, I think, is 0.1,
It's
something like that.
very fast
It's
rotating.
really very fast rotating. So our simulations have much larger Rossby number at the surface. So basically, potentially, the mechanism that we have seen, so magnetic pumping or magnetic compression of field lines by convection, can explain the mechanisms, for example, that are responsible for the generation of magnetic dipoles in the work of Hydra. This is the context that
Okay, so the difference you would say is because you basically consider same law of stars, but at different rotation already.
we are in slightly different parameter
So
regimes.
it's a more slowly rotating star.
Yes. I would say so.
Any more questions? Papa?
Another question. If you rotating, see the spiritual information, taking rotation,
Yes.
this is modified expression of super. And on the other hand, you introduce a beautiful ring living up here.
Yes.
So now there is some observation to the same something where I was. When all this interaction was they in terms of essentially not expressed. The important observation issue very useful for we are graduation in order to find
I think it's a really good point because indeed this is a big question currently in asteroseismology. The influence of magnetic field on the change in frequencies of stellar oscillation that are observed. And so in this respect, well, I'm not an asteroseismologist, so I have not been working on that yet. From what I know, that of course different magnetic topologies, magnetic topology will affect asteroseismic frequencies because it will change the linear stability problem or wave equation problem for for them. And so it would be really interesting to take this to take these magnetic topologies and to see which frequencies they're actually producing. So this would be really promising research direction to do in the future.
It's, our- This one is really, amazing.
Mm. Yes.
One last question. I have one. So these are very interesting points. There are many challenges and problems here to study. I wanted to ask you, which one is your favorite?
I think you mean with respect to the future or
Yes.
with respect to the future work? I think the most interesting point is of course the local activity. Because since you have models that can really predict the temporal evolution of magnetic fields, we can look at how and we should look at how this magnetic field affects the time variations in the activity indices. I think this is what the data.
So thank you very much. And thank you everyone for coming, participating. If you want to continue the discussion, we have now at 2 o'clock, we have lunch in Labrador. I don't know if you know this is very, very near, and we can meet at the entrance if you want. It's, let's say in 15 minutes, 15 or 20 minutes. And we can go to the restaurant. Okay.